This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. We're diving into a fascinating debate today, the existence of Planet 9, or as this paper calls it, a possible Planet X. The hunt for this elusive world has captivated astronomers for years. So what's the current state of play?
The evidence is circumstantial, but intriguing. Several studies have pointed to a potential gravitational influence on distant trans-Neptunian objects, suggesting a large, unseen planet.
So it's not a direct sighting, but rather an inference based on the orbits of other objects?
Precisely. The gravitational tug of a massive planet could explain some unusual clustering in the orbits of these distant objects.
And this paper, Orbit of a Possible Planet X, offers a new perspective on this, doesn't it? Let's talk about the stability of these distant TNOs. Why is that crucial to this whole Planet X hypothesis?
The gravitational effects of a Planet X would take a long time, on the order of a gigayear, to significantly alter the orbits of these objects. Only those TNOs that remain stable over such timescales are relevant to the analysis. This paper uses long-term N-body simulations to identify these stable objects.
Right, so you're not just looking at current positions, but projecting orbits far into the future.
Exactly. We're using sophisticated simulations to determine which TNOs are likely to remain on stable orbits for billions of years. This allows us to expand the sample size significantly compared to previous studies.
This expanded sample size is a key contribution of this paper, right? How does it change the analysis?
Absolutely. Previous studies relied on smaller samples, making it harder to draw definitive conclusions. By including a larger number of stable TNOs, we can perform more robust statistical tests. We use the Kuiper test to look for clustering in the longitude of perihelion. Oh.
I see. And what did the Kuiper test reveal?
We found statistically significant clustering in for TNOs with semi-major axes greater than 170 AU at about the 3 sigma level. This is a strong indication of a gravitational influence.
But not in other orbital elements like inclination or argument of perihelion?
Correct. The clustering is specific to the longitude of perihelion, which is a key piece of evidence pointing towards a Planet X.
So you ran N-body simulations to model the effects of a hypothetical Planet X. Can you walk us through that?
We ran 300 simulations varying the mass, semi-major axis, eccentricity, and inclination of the hypothetical planet. We also included the giant planets and a disk of test particles representing the Kuiper belt.
Yeah. And what were you looking for in the simulation results?
We compared the distribution of in our simulations to the observed distribution of for the stable TNOs.
Right.
We calculated likelihoods to find the best fit parameters for the hypothetical planet.
And what were those best fit parameters?
The best fit model suggests a planet with a mass of around 4.4 plus or minus 1.1 Earth masses, a semi-major axis of 290 plus or minus 30 AU, an eccentricity of 0.29 plus or minus 0.13, and an inclination of 6.8 plus or minus 5 degrees.
How do these results compare to previous estimates of Planet 9's parameters?
Our results differ somewhat from previous estimates, particularly in the mass and inclination. Our planet is slightly less massive and has a lower inclination than some previous estimates.
Why the discrepancy?
Several factors contribute. Our stability analysis is more rigorous, our sample size is larger, and we focus solely on the longitude of perihelion clustering, which is the most statistically significant feature.
How statistically significant are these new findings?
Very significant. Only a tiny fraction, 0.06% of the Brown and Badigan Planet 9 reference population produces probabilities within 1 sigma of our maximum likelihood. This suggests our model identifies a distinct region of parameter space.
And where might this Planet X be located?
Based on our simulations, the planet is most likely to be found near the ecliptic plane, primarily in the northern sky. A significant portion of this region will be surveyed by the Vera Rubin Observatory's LSST.
What are the prospects for actually observing this planet?
The planet is predicted to be within LSST's detection limits, so there's a good chance it could be discovered in the coming years. However, it's important to note that the search is challenging and there are limitations.
What are some of those limitations?
The planet's predicted brightness is relatively faint, and its location is uncertain. Also, there's always the possibility that the observed clustering is due to other factors, such as observational biases.
Could the clustering be due to resonances with Neptune rather than a planet X?
We investigated this possibility. While resonances can cause some non-uniformity in the distribution of the effect is too small to explain the observed clustering. The observed distribution has a single peak, while resonances would produce two peaks.
Are there any other potential explanations for the observed clustering?
Observational selection effects are always a concern. However, our analysis suggests that these effects are unlikely to be the sole explanation for the observed clustering. The difference in distributions between stable and unstable TNOs is statistically significant.
What are the next steps in this research?
Further observations are crucial. LSST will significantly expand the sample of known TNOs, allowing for more robust statistical tests. More detailed simulations, incorporating additional factors, could also refine our estimates of the Planet X parameters.
What are the implications if a planet X is eventually discovered?
It would revolutionize our understanding of the solar system's formation and evolution. It would also raise new questions about the nature and origin of the outer solar system.
And is that discovered?
Then we'll need to explore alternative explanations for the observed clustering in It could be a statistical fluke, or there might be other, as yet unknown, gravitational influences at play.
You also analyzed the eccentricity vector of the TNOs. What did that reveal?
The eccentricity vector points towards perihelion. By analyzing the mean eccentricity vector for stable and unstable TNOs, we found a statistically significant difference, further supporting the hypothesis of a gravitational shepherd. The stable TNOs show a much stronger alignment of their eccentricity vectors than expected by chance.
So this strengthens the case for a real effect rather than a selection bias?
Yes, the 2 order of magnitude difference in the probability of exceeding the observed mean eccentricity vector magnitude between stable and unstable TNOs strongly suggests a real physical effect.
You also performed a survey-specific analysis focusing on TNOs discovered by OSOS, DEIS, and ST. Why was that important?
This helped us to assess the potential impact of observational biases on our results. By comparing the distributions of orbital parameters for TNOs with different semi-major axes discovered by the same surveys, we could better isolate the effects of a potential planet X from survey-specific selection effects.
What did this analysis reveal?
It showed that the clustering wasn't solely due to survey biases. The results remained consistent across different surveys.
That was a great discussion. Thank you for sharing your expertise.